Welcome to the Explainer. So today we're going to talk about something really cool, a piece of AI that actually learns to fix its own vision before it even tries to figure out what it's looking at. Yeah, it's a network that learns how to look, not just what to look for.
All right, so let's just dive right in. We're going to start with a really basic but huge challenge that a lot of AI models face when they're trying to, see the world like we do.
I mean, it seems pretty simple, right? You and I can recognize a cat whether it's upside down or way off in the distance. But for an AI, even for some of the best convolutional neural networks out there, well, these simple little changes, a bit of rotation, a different scale, a shift in position, can be totally confusing. And that right there, that's the core problem we call spatial variance.
Just imagine for a second, you have to teach a network what the number 7 looks like. Okay, easy enough. But then you also have to teach it what a slightly tilted 7 looks like, and a zoomed-in 7, and one that's shoved way over in the corner of the picture. It's so inefficient. This forces the main network to do double the work. It has to figure out where the thing is and what the thing is, all at the same time. You just know there's got to be a better way to do this.
So how do we get around this? Well, the answer is actually really clever. It's a special little module that works kind of like a preprocessor, but it's built right inside the network itself.
And that brings us to the hero of our story today, the Spatial Transformer Network, or STN for short. Think of it as this small, specialized gadget that you just plug into a bigger network. Its one and only job is to look at the incoming image, see how it's all twisted or off-center, and just fix it. And it does all this before the main network even gets a peek. This completely frees up the main network to focus on what it's really good at, the actual classification.
And that's the really brilliant part. The STN is an active, intelligent piece of the puzzle. It literally learns the best way to transform the images to make the whole process easier. This isn't some fixed, pre-programmed step we set up beforehand. Nope. It learns and adapts as it trains. It gets better over time.
Okay, so how does this magic actually work? Let's pull back the curtain a bit. It can really be broken down into 3 clear, distinct steps. It's not just one big black box. It's a super clean, logical pipeline.
So first up, you have the localization network. You can think of this as the eyes of the operation. It finds the important part of the image. Then you have the grid generator and the sampler. These two work together like the hands to actually perform the transformation. So let's zoom in on that first step, the eyes. So everything kicks off with this thing called the localization network. It's basically a targeting system. It's a little mini network that scans the whole input image and then spits out a set of parameters. Think of them as instructions that say, okay, here's where the important stuff is, and here's how it's tilted. All right, so those parameters get fed into the next layer. And this is where it gets really cool. All of that complex visual info gets boiled down to just 6 numbers. That's it. These 6 parameters, they define the exact transformation that needs to happen, the rotation, the scaling, the skewing, the whole shebang, to fix the image. And that brings us to the final piece of the puzzle. The network uses those 6 numbers to create a special grid, which is basically a map for how to warp the original image. Then, something called a sampler comes in. It uses that map to grab pixels from the original before image and build the brand new corrected after image, and boom, it's perfectly centered and scaled.
Okay, but the big question is, does this all actually work in the real world? I mean, it sounds good in theory. The key is that the whole system is trained from start to finish all at once. We don't sit there and tell the STN what a good transformation is. It has to figure that out all by itself, just by seeing if the changes it makes help the main network get the right answer more often.
So to put this to the test, we're going to use the classic MNIST dataset. And it is absolutely perfect for this job. Why? Because it's packed with thousands of handwritten digits that are naturally rotated, scaled, and off-center. It's the exact kind of messy data that an STN is built to clean up. And wow, the results really do speak for themselves. After just one single pass through the data, one epoch, the model is already hitting 94% accuracy. Pretty good. By the 8th pass, it's up to 98%, and by the time it gets to epoch 13, it has pretty much mastered it. This is so important. The network isn't just learning to recognize digits, it's learning how to change them so it can recognize them better. I mean, look at that. A final accuracy of 99% on the test set. That's just incredible. It proves that letting the network actively mess with its own input gives its performance a massive boost. What you end up with is a model that's way more robust and super accurate. But hey, numbers are one thing, right? Seeing it with your own eyes, that's when it all really clicks into place. So let's actually visualize what the STN is doing to these images.
Okay, so take a look here. This is a batch of images from the test set before the STN gets its hands on them. And you can see it's kind of a mess, right? The digits are all over the place. Some are tiny, some are huge, some are leaning over. This is the exact challenge the network is up against.
And now, here are those exact same images after they've gone through our trained STN module. Just look at that difference. It's amazing. The network has learned completely on its own to zoom in, to center, and to straighten out every single digit. It's serving up this perfectly clean, standardized view for the next part of the network to analyze. So this really paints the perfect picture, doesn't it? Before, you've got this messy, unpredictable data that's a real headache to classify, and after, you've got this beautifully aligned, clean data that's a piece of cake for the network to understand. The STN is basically an automatic data cleaner that learns how to do its job instead of being told.
And really, this is the main takeaway. If you remember one thing, it's this. Traditional networks only learn what to look for, right? The specific features of a 7 or a 3. But when we add a spatial transformer network, we give the model a whole new superpower. It also learns how to look by actively fixing its own input to get the clearest possible picture.
And that just leaves us with a really fascinating thought, doesn't it? We've just seen an AI that learns to correct its own vision. So, what's next? Could a network learn to automatically filter out distracting noise? Or maybe even learn to decide which parts of a huge, complex scene are the most important ones to pay attention to? This whole idea of networks that can actively control and clean up their own input, well, it's incredibly powerful, and it really opens up a whole new universe of possibilities.